Hello there. Thank you so much for joining us today. My name is Brian Fromm, and I'm in the SUSE Global Alliance team for HPE. And now I'd like to introduce my co-presenter.
Thanks, Brian. This is Brian Gardner. I've been with SUSE for about 8 years. I work on the Alliances team as well with Brian, and I am a senior technology strategist. I work with hardware partners, software partners, and embedded partners. Back to you, Brian. Start kicking it off.
Thanks, Brian. So this is what we're going to be talking about today. Just to show you a quick overview. Let's dive right into it. So what is enterprise performance computing? Enterprise performance computing is a term started by our friends and partner company Scilabs to represent these modern workloads that companies are using in today's digital transformation. These workloads are open source technologies that help companies build artificial intelligence, machine learning and deep learning, big data and analytics, edge and IoT, video processing, and many other technologies like this. And we'll dive into some use cases and some examples and a little bit of architecture around what these modern workloads look like. So I mentioned digital transformation. Really, why are companies looking at these modern workloads? Why does a company start exploring artificial intelligence, for example? Digital transformation is really a concept that companies are realizing, in particular with the complexity in our world today, that they have to get their company to become more agile at producing services that are on the internet for their customers. And there's really two aspects to this digital transformation world. There's the operational efficiency aspect, which has to do with tuning the IT infrastructure to be more nimble and more agile in its ability to deliver services inside the company and outside of the company, as well as the ability to then build applications that move a company's typical product and service offering online into a much more digital offering. And there's some great resources on digital transformation. Of course, you can use Google, but you might also look at MIT's Sloan Education organization, and there's a book called Designed for Digital. And that's a great survey and use case study of digital transformation and how companies are wrestling with moving their companies forward in these digital transformations. So with that, I'm going to pass it over to Brian Gardner.
Thank you, Brian. And, you know, on this slide and whatnot, you see the kind of assimilation or the similarity between enterprise performance computing and high performance computing. And Brian, if you want to go on to the next slide. And this is actually where this comes from a lot. We've talked to a lot of customers and we have a big play in this space, right? If you go look at the top 500, a significant portion of that is based on SUSE operating system and whatnot. But those customers came to us and they started talking about how do we move some of that into the enterprise space and take advantage of all the things we know how to do. And the things they already know how to do is they know how to do parallelism. You know, they use message passing interfaces in a parallel fashion. They have clusters of computers, and you can see from this picture, it could be hundreds or thousands of nodes. Typically, when they build this, they rely on the specialized functions of a CPU or even other chipsets. And that's where they plant their foot to get started and take advantage of that. Underlying that, again, because of the message passing interface, they want to have a very high-speed interconnect because we're talking to thousands of systems, right? And maybe hundreds of thousands of cores. And also on that high-speed interconnect, there's a back-end storage because, let's face it, there's persistence. I have to read data, I have to calculate things, and I have to push data output back out. Next slide, please, Brian. So if you were to look at an architecture of HPC, and you'll see a lot of the green boxes here that kind of overlap with products and functionality that we provide from SUSE. But let's start in the middle there with that whitish, that light gray box that talks about the administration. That's where the head node of a cluster for HPC is at. That's what users interface. That's what they talk to launch a job. And then all those gray boxes to the next are where all the compute happens. Right, so there's compute nodes, the tens, hundreds, thousands. Some of those maybe have certain kinds of processors or certain kinds of functionality or everything like that. But again, below that, there's that message passing interface on that low latency fabric to make all those connections happen. That's how they do that workload. That's how they use it. And on the back end, you see that there's that high performance storage. And the classic one that's often used is Lustre, right? And it's a very low latency. It's a very high performance storage engine because again, thousands of things are pounding on it all the time. Over on that right-hand side, again, there's all that software that you need to make all this possible, like workload management and scheduling and things like that. That's how an HPC cluster is set up. So as we go down the path of talking about enterprise performance computing, you'll see that this kind of becomes very similar, and we're just going to substitute blocks, but we're still going to rely on these things. Next, please. Some of the characteristics of enterprise performance computing, it really does depend on the workload. And one of the popular things, again, the outgrowth of the HPC space is in the analytics space. And that could be artificial intelligence, it could be machine learning, it could be deep learning. And what do you need to do that most effectively and the quickest? You might need the parallelism, the huge, multiply the number of cores that I mentioned before by another factor of 10 to 100 again, because you're doing all this stuff in parallel. And yeah, I want clusters of all those things again. Or I might be using a specialized like field programmable gate array or a tensor offload processor or vision processing units. But again, I'm going to rely on, and I need high-speed interconnects. I really need to have that high-speed data throughput so that I can, again, read the data, perform the calculations, produce the outputs, maybe modify the data. All of those performance requirements have just scaled up even more. Next slide, please, Brian. If you were to look at something like a machine learning workload, so that's the ML space, again, what they rely on is that parallelism that's in the GPU, the multiple numbers of cores. If you look at a neural net, which is almost the deep learning side of AI, ML, DL, that's how it's set up. You basically have an input layer that reads all the data. You have countless hidden layers, and that's at the discretion of a data scientist to come up with how those are configured, how many there are, how many weights are set up, how things are hidden, all those things. Then you have an output layer. Those rely on all of those cores that are in a GPU. So the faster you go and the more specialized, I can take advantage of that. And it was interesting in the past, I saw one of the GPU providers and one of the CPU providers, they always pointed at each other and said, you're on the wrong side of the bus. They're talking about the IO bus. Well, the beauty of it is we can take advantage of both sides of that bus now. And especially in the enterprise performance computing space, you can take advantage of both. You can segment workloads to go one place or another, and you can take scale off the limits, okay? In addition, there's also other hardware things that have come out, like NVMe and whatnot, that gives us way faster storage and capabilities like that. Next slide, please. And if you think about those performance characteristics and also this enterprise computing, performance computing, it can scale and be distributed kind of everywhere. We could go all the way out to the edge, and we can take advantage of a GPU-centric single board computer way out there. And I can do the machine learning there on data that came from IoT and sensors. Again, I could take advantage of things like NVMe or those offload processors, field programmable gate arrays, custom sensors, those cameras that are all over the place and do image recognition and things like that. So you can see how we're taking what we learned in the HPC space, we're growing it into more and more workloads, and then we're distributing it back out to the edge. So if you were to go to the next slide, Brian, I'll go over the enterprise performance computing architecture, which feels very parallel to the one you saw a minute ago for HPC, but I'm going to substitute some parts in there because of that distributed computing that you might have. So instead of just relying on classic bare metal workloads, you might do everything in a container fashion. And with something like that, SUSECON platform, which provides a Kubernetes distribution, that may be the way that you do this. So you still have that admin node, but you still may have many hundreds of compute nodes And those are those clusters in those darker gray boxes. But some of them may have GPUs in them. And you just label that in Kubernetes when you do the scheduling of a workload, because I want to land on a node that has a GPU. Okay, done. Next question. But one of the things that you also get back is you may not need as high a performance inherently for like a data lake or something like that to access the storage. But what you need is more ways to access it, because again, I might be ingesting data from somewhere else. I might be working on the workload, and I might be producing outloads like even a machine learning model to hand off later. Over on that right-hand side, tools like our Cloud Foundry-based SUSE Cloud Application Platform, that gives the developers the answer of, just like in every traditional workload, yeah, you might have a database, but what's the first thing you do is you create all the SQL statements? Well, in this context, with Cloud Application Platform or something like that, I can create a workload that runs on top of TensorFlow, that runs in a container that lands on this cluster. And with all of that, now we have all those pieces. We can do enterprise performance computing, and now we can start to talk to the data center folks and start pulling them in saying, can I leverage the data that you have too? And with that, Brian, let's go on to the next slide, and I'll just talk a little bit about bottlenecks. So one of the key bottlenecks in this space is data pipeline, because again, I said there could be something on the edge, and that could be a device that's in the middle of nowhere on an oil pipeline, okay? Or it could be somewhere totally different and it can only transfer like from an oil rig or something like that. So there is that data pipeline, and you have to take into account all of the aspects of that, of the integrity of the data, cleansing the data, making sure that it's came from a device that you trust. It's not somebody's just Bluetooth device that walked by and gave you an answer that you thought was useful. In the data analytics space, again, they are going to want to use a scalable storage thing, right? Because I've got to scale across that entire cluster and across potentially multiple geographies. And that high scale memory is with like NVMe and whatnot, gives me that ability to react very quickly, do the workload in memory, and then go off and do another workload. Like we mentioned earlier, it could be video cameras or audio, things like that. So now you can see bandwidth issues. And just like, you know, we're doing a web recording here and whatnot, it depends on where you're at, because we're all distributed. We all have different bandwidths of getting that video to me, but I still have to react very quickly. So now I'll hand it back to you, Brian.
Thanks, Brian. So let's talk a little bit about some of the workloads and the specific aspects of those workloads that are in this category we call enterprise performance computing. So we've already touched on these, but I'll just kind of go through and reiterate and talk about a few other workloads. Of course, AI and ML and DL are very common and you know, on everyone's mind today. It's a fascinating space. Big data and analytics, video capture, we've talked about all that at the edge, and in the data center, of course. All these big data and AI activities can happen in either of those places, as Brian mentioned. Security monitoring and response, that's a very interesting one. That's sort of an edge-like application that can happen out at stores, and often involves video transcoding and processing and some AI even to analyze the video to understand what's being seen from that camera. Way more sophisticated than the old days of just capture video and somebody looks at the whole video to analyze. Digital currency and blockchain are another category that has become popular in the financial industry and elsewhere. High throughput transactions, we see that of course in the financial industry, but elsewhere as there are other domains where high throughput transaction and high throughput data streaming is part of enterprise workload. Brian mentioned autonomous vehicles, and we'll talk a little bit more about those kind of architecturally. So that's a fascinating space, and that really, in my mind, pulls together. It's a workload that pulls together all these technologies and some of the aspects that Brian's already commented on. Robotics, you know, we've all seen how robotics applies certainly in a manufacturing setting, but elsewhere, of course, moving even as far as into the home today. And that's just some of the workloads. There's many more workloads that fit into what we call these enterprise performance workloads that involve these modern technologies, modern open source technologies that companies are experimenting with to provide services to their customer. So let's talk a little bit again about machine learning and what some of the characteristics that that bring that back into the enterprise space. So, you know, Brian kind of summarized some of the machine learning characteristics from a performance standpoint, but we'll talk about it from a more like how does a company approach machine learning. So we'll just touch on this a bit. So certainly there's the definition of the model, right? And that's something that falls into a data scientist category, someone who's a specialist in the model of machine learning or deep learning. So there's defining, well, what is that model? How do I define a model that distinguishes between cats and dogs, or between good people are entering the store and dangerous people entering the store, perhaps. There's data sets, right? There's just the analysis of data, and that's often they're data specialists, people who are good at understanding the plethora of types of data and how to analyze the data and turn it into a common set of data that applications can then operate over. And we'll talk about tools in a little bit that help us with these activities. There's, in AI, of course, there's training and inference, right? Two different sides of the work that goes into the building of the application. Of course, training is the feeding the machine learning or deep learning algorithm or model, the training data, right? That allows it to start understanding the statistical input or curve that defines the best cases for the algorithm that's being defined. And then inference is really the side that's doing the runtime, right? The inferring the actual information that the application wants to know, like what sort of person is walking into our store. And all of that is bundles into how companies build algorithms, and that's really a software development activity, and again, we'll touch on some of that quickly. All right, so let's move from the machine learning AI world to the edge and the IoT or industrial IoT world. In edge and IoT, a lot of times people think of edge as out there, right? Some device is out there, right? Maybe it's a smaller device that does something like Brian mentioned in an oil field. But there's a couple of characteristics that are more enterprise in the way of thinking about this. First of all, edge is really an end-to-end kind of application need, right? We don't just build an application at the edge and that's the end of it, because what are we going to do with the data when it's generated out there? So really it's a matter of there's something happening out. Again, let's just use the oil field example. There's something happening on an oil rig. So we do have sensors and other types of collection devices that pull data in to the application, and then we need to do something with that data. So often there's some edge, Brian mentioned this before, some edge processing that could involve machine learning and deep learning right at the edge. So that takes these devices from small, what we think of as small, lightweight, tiny devices to kind of enterprise class devices. And when you look at the computing capability that companies are putting out, hardware vendors are putting out, we're seeing server class computing moving to the edge in small form factors and in hardened form factors that can run safely in an oil field, for example. So that's pretty fascinating. But again, back to the company, and they're building the edge application. So they're pulling then that data that maybe is pre-processed from the edge into the data center. So that's, like Brian mentioned, there's bandwidth requirements to bring that data into the data center. And then from a development standpoint, we have the model of how do we build this end-to-end application that I mentioned. And the old world of building applications was we design it all up front and then we deliver the end result application. Well, that just doesn't work in such a highly specialized and complex world like enterprise performance computing. So what we really need to do is break the problem down and take a much more agile approach to the way we build applications. We want to prototype and discover potential performance bottlenecks or potential application challenges like, well, I just mentioned performance, but maybe just the the ability to do the level of AI that we need at the edge. And maybe that's a challenge that the application team needs to discover and then solve. And so there's moving from a prototyping phase to a piloting phase where we're installing this end-to-end application and really experimenting with it at scale, but not at full scale, at just beginning to ramp up the scale. And you can see, right, in an edge application how scale could be millions of transactions per day, right? Or streaming video all day long, right? In a store that's open 24/7, or sensors on the oil rig that run all day. So again, we need to build up from a small base and then pilot at a smaller scale as we begin to build closer to a high scale, fully throughput end-to-end application. And then, of course, there's the internal data center, that what we think of as the common IT operations side of things, where we have core and cloud infrastructure, right? Clusters of typical computing that might have databases and their own machine learning and data and deep learning algorithms that run in the core. And the cloud infrastructure might be ways to present all this information to the customer, right? That might be the most convenient way for a customer to interface with the end resulting application. So you can see what I just described is pretty complex, right? It's an end-to-end application to really get to an enterprise, a production enterprise performance computing workload. Okay, so now we're going to talk a little bit about the tools that companies use as they build this example that I just went through, or enterprise performance computing applications as I just described. So first, we're going to start with the development side. On the development side, we've talked about in AI, the GPU performance acceleration as key to the way AI algorithms work. So to do that, we don't just dump a workload on the GPU, we have to do GPU programming, and that's done through these common toolkits like TensorFlow or PyTorch or Kubeflow, which is TensorFlow in a Kubernetes containerized environment. And those are interfaces or programming frameworks that development teams use to program the GPU capability, the models that the ML or DL are running. In the analytics world, we have tools like Hadoop or Kafka or Spark or SAP Data Hub that help us with streaming data from, for example, the edge into the core data center, or in particular with SAP Data Hub, we have data coming from a plethora of different sources that are all different formats of data. And how does the application deal with that? Well, it's way too complex to write code for hundreds of different types of sensor data. Instead, we need to massage the data into some sort of common format that the applications can then process and then move on to another stage in a pipeline of analysis work. And SAP Data Hub is specialized in that capability and bringing together that data and massaging it into specialized formats and then setting up the pipelines that I just mentioned. In terms of workload development, as we build up the actual application itself, customers are using tools like from SUSE, the cloud application platform that Brian mentioned, which helps us build the containers that then we'll use to deploy the workloads. And they may do that using AI toolkits like Jupyter. They certainly use continuous integration and continuous deployment tools like Jenkins. We use Git for managing the code, right, and versions of code in a distributed world. And that's just touching the beginnings of as a developer, the number of tools that development teams really end up using to really solve their development challenges. So there's so many more that we could talk about. We could probably do a whole presentation just on development tools themselves and how they're used. In the storage world, as companies use these modern workloads in open source and open source technologies, they do that in a containerized environment. And that's because containers really help them to create these applications that are easily deployed across this diverse set of machines that we've talked about. In an edge example, I've got data center, high-end data center machines, and I've got low-end processing out at the edge. And those environments are different in terms of the platforms and the tools that reside on them for all sorts of reasons, performance, support, cost. So in doing that then, when I build up a storage capability, I want to use a containerized capability to get to my storage. And so in containers, there's a capability called CSI, which is an interface, basically a common interface to the containerized storage that I can then interface to, like SUSE's SUSE Enterprise Storage for doing streaming data into my application. And so these containerized interfaces really make it simpler for, as I build my workload, to program to a containerized environment. So it moves me up the stack of developing in containers for a containerized environment. Okay, well, let's switch from the development side to the operations side. We talked a bit about containers, and we'll go a little deeper there. So these containers are really using several different types of technologies, right? Everybody's familiar with using the word Docker, but in enterprise performance computing, we also use a technology called Singularity, which is a container technology, and that really came originally out of the high performance computing world, but applies very much in the enterprise world. Many companies who are doing artificial intelligence are using Singularity as their chosen container environment. And so it's important for companies to have the flexibility to choose the type of container technologies they use and to know that they can deploy these containers onto a runtime environment that can handle that isn't just one container technology like Docker, but has a container runtime interface like SUSE's CAS platform uses CRYO, uses a standardized container runtime interface to allow more flexibility in the kinds of container runtime engines that can then be run. And that gives these customers the flexibility to choose the container technologies that they'll use as they build up their workloads. And then we move from the actual containers that the developers are using and that the operations side is managing to the orchestration or the management of those. So Brian early on mentioned Kubernetes as the platform of the way containers are run. And in the past 2 years, Kubernetes has really won the mind share and is the de facto standard for container runtime management, or orchestration is the term we tend to use for that. And SUSE's CAS platform uses Kubernetes as the base for that container runtime orchestration. And what that allows companies to do is focus on a single technology that then they can get good at managing across their enterprise. Again, they can use Kubernetes in the data center, they can use Kubernetes in the edge, Kubernetes in the cloud, and they can get all of that capability from a single vendor like SUSE. Those same kinds of needs apply to storage. So as a company begins to look at, well, I'm moving my workloads across my enterprise to the edge, to the cloud, in my own data center, I need a common interface to the data that I'm producing in this wide set of sensors and different data sources. So how am I going to store all that data? And this data is going to be, by its definition, high scale. It's going to scale to very large, potentially even petabyte and exabyte levels. So how am I going to manage all that data? Well, SUSE Enterprise Storage gives me the flexibility to deal with data, whether it's block data, file system data, object data, all potentially streamed from different sources, and then managed at high scale across a cluster. And so that's a common technology that companies are using in enterprise performance computing to deal with data at scale. And one more comment here, and this is, again, another topic that's probably a pretty big topic, and I'm only going to touch on it, but IT operations teams are very comfortable with their virtualization, all right? In the past 10 years, companies have really focused on virtualization as the place to virtualize an application from moving it from bare metal into a virtual machine. And today, companies are really trying to wrestle with how do they bring together virtualization, like virtual machines, with containerization. And that's something that SUSE is very strong at. We have, as we've talked about, SUSECAS platform, and we can run this on top of a virtualization environment. We can run containers in virtual machines. And so we help companies really navigate this blend of how do they manage their virtualization with their containerization, again, at scale. All right, so I've touched on a lot of these, but I'm going to touch a little more deeply in some of the tools that SUSE provides to customers to do these both development and operational side. So we've talked about TensorFlow and PyTorch and kubeflow. These are all tools that are available in SUSE Linux Enterprise Server and are tools that customers are using today to do machine and deep learning. We talked about streaming data through Hadoop or Kafka or Spark, and using a tool that manages the data, like to convert data into a common format like SAP Data Hub. Again, these are all tools that are available on SUSE Linux Enterprise Server. There's this SUSE Linux Enterprise Server itself, right, which can run across this wide range of computing platforms. Whether it's ARM or Intel or IBM Power or out at the edge in smaller form factors or in very high form factors like what often customers do for a large in-memory database and high transaction processing databases through SAP in the data center. So these are all tools that companies are using today from SUSE to help get their job done. SUSE Cloud Application Platform then is really a development tool that helps companies manage the containers that they're writing for these environments so that it's easy for the development team to work in this DevOps model where they're working much closer with the IT operations teams. And the IT operations teams can define policies that the development teams can then leverage to deploy their applications easily. And I mentioned SUSE Enterprise Storage as a base and a high-scale platform for being able to pull together very large data from these enterprise performance computing workloads. Okay, I'll touch quickly on these same tools in the enterprise, the IT operations side of the space. So we talked about Docker and Singularity and SUSECAS platform as the technologies that companies leverage to build a base for managing the runtime environment for their container workloads. And we talked about Kubernetes, which is the orchestration component in SUSECAS platform as the de facto standard for the way orchestration is done in the IT data center today. And I also mentioned this can happen not only in the data center, but out at the edge as well. And then again, companies are working with both virtual machines and containers, and they're trying to mix these technologies together. And so SUSE creates a tool called SUSE Manager, which helps companies to deal with these operating systems and the virtual machines and container runtime engines all at scale across the enterprise. So we need a tool that keeps track of where are all these machines and their operating systems and their workload components, and do I have the right versions of code on these machines? Do I have the right patches to make sure that I'm building a secure environment? So SUSE Manager is also a key piece of managing the complexity of building an enterprise performance computing workload. Okay, with that, I'm going to pass it back to Brian to talk a little bit about some use cases and some examples of these use cases for enterprise performance computing.
Thank you, Brian. And why don't you challenge me and tell me what kind of use cases you'd like to hit? What are the first two, or which one you'd like me to go over first?
Sure. So first, I'd like to really focus in on a healthcare example, and I'd like to leverage your knowledge in working with CT scanners and the types of technology that goes into a CT scanner and the types of challenges that happen architecturally at this type of application.
Sure. Let's start there. So, one of our customers does do this, and we worked with them for years on this. It used to be that there was a device inside the CT scanner that was the collector of all this data, right? And think about something like that magnet that's spinning around fast enough and capturing a complete view, a 360-degree view of your heart within one heartbeat. And imagine all that data that's coming back to you and you're figuring out what it is. Then across the aisle, on the other side of the partition, there was another one that was rendering it so that the technician could look at it and say, yep, we got the right part of the body, we got what we expected to do. Then you had to go to the next step of, how do I analyze it? How do you analyze the radiologist and whatnot? Well, what we've seen is this enterprise performance computing has kind of gone into this space now. So what they've done is they've minimized what they need at that sensor, which is, a very expensive sensor, very specialized sensor, but they're actually taking the data and sending it to a more centralized place where they do the rendering. And so the operator still is getting that technician is still getting the picture of, yeah, I got the right thing, but immediately they're starting to run analytics on it and looking at the results and saying, okay, this is what I see, this is what I need, blah, blah, blah. And then they hand it off to, the doctor and whatnot, but they can also provide not just the image itself and the reconstructed image, but they can also provide analytics of, oh yeah, you were looking for this, but here's another thing that we found here that may collaborate with the symptoms the patient is having. That's what's happening in this space. And it's that data center may be very nearby in the hospital, or maybe centralized for a bunch of hospitals in the same city. But all of this can happen, and they're using enterprise performance computing technologies to do all this. Let's go on to the next one, Brian. And just to kind of describe that, show it in a graphical form, because it's like edge to core to cloud and customer, although the customer could be the doctor who at the end of the day is pulling up his cell phone and seeing the reconstructed render in the image, and with the side metadata of, here are the analytics, here's the machine learning that I ran, here are the things that I see that you might want to take into account before you call the patient back and say, yes, you have a heart valve problem, okay? But that edge device has really become the CT scanner, and then that local hospital database where a Kubernetes cluster is running and running all those analytics. And then, of course, the data has to be centralized, via a PAC system or something like that. And some of this data could be done and moved into the cloud because, let's face it, a patient could be in geography A, like the US, but then something happens when they travel, although they can't travel right now, but, due to COVID and whatnot. But if something happened to them overseas, how does that doctor access the data that they need? You can do all of this in the healthcare environment with an enterprise performance computing thing. Let's go on to another use case, Brian.
Sure.
So we'll go ahead and skip this slide for right now, because that's just very detailed, and I want to make sure that, folks, you can look at that, but that's like the underlying pieces of each one of those things, and it's kind of overwhelming, but I just want to show that it's there. All right, so what if we did an autonomous vehicle instead? Okay, if you think about it, you look at the sheer number of sensors that you're involved, and I've taken a webinar where they called it sensor fusion. Think about how many cameras are probably around the perimeter of your car, and LiDAR, and all of that sensor data is coming into you, and you're trying to figure out how to react to, is that a person at the crosswalk ahead of me? Do I need to stop? Or are they waiting for the walk light and things like that? You've got to take into account all of those pieces and put those together like instantaneously. We're hoping that they do it instantaneously, right? Because we're the ones sitting there in the car. But then there's also the telemetry data. If you plug into the CAN bus, right, that's in your car, and you can get the computer output and the codes and whatnot, what's the first thing you need to do is you need to react to the code, because it's very summarized, right? It says engine 4 or engine cylinder 6 might be misfiring. Well, therefore, if they sent all that data to the maintenance center, they could notify the customer saying, hey, I think you have a coil problem, or you have a spark plug problem. You might want to make an appointment and get it come in, or, obviously folks like me, we would go fix it ourselves. But that could all happen. And then that data of capturing, in a GPS standpoint, the data comes to me of where I'm at and how to react to it while I'm driving, and also the answer heading back the other way of, oh, I'm in a traffic jam, so basically if somebody else is on another path this way, guide them around that so they can get there faster, right? All of this is enterprise performance computing. It spans everything we just talked about. And with that, Brian, I think I'm going to turn it back over to you.
Yep, thanks, Brian. So I'm going to jump into just some of the key success factors that go into a company employing enterprise performance computing in their environment, their data center, but out to the edge as well. And first, it's really the architecture or the enterprise architecture that the company has to wrestle with to understand how to build this application at scale, right? All of these technologies we've talked about today, they're dealing with problems at scale. Millions to hundreds of millions to even billions of interfaces or users, and very large scale data that has to be managed. So we have to develop models by which we can build up the application capability little bits at a time, right? We can't just solve the whole problem at once. We have to prototype and experiment and then build that up and see how it deals with scale. And so there's definitely kind of the crawl, walk, run approach of prototype, pilot, grow, test. And so that's very much a design for scale model that's built around agile methodologies. And then another key aspect to that environment is that the environment really isn't static. The environment's dynamic, right? You don't just put a data center together and put some machines out at the cloud and at the edge and say, there, I'm done, right? These change, right? Your cloud instances grow and shrink, your edge capabilities change over time, even the data center changes over time. So your application isn't static, and that's an important aspect. And again, agile methodologies really help customers to wrestle with the dynamic nature of these applications. We've talked a lot today about performance, and performance is key, right? That's why we've called this enterprise performance computing. It's really the heart of the challenge here, right? To run AI at the edge is a performance characteristic or challenge that we need to solve. And so how do we do that? As engineers, we need to find key bottlenecks. We need to experiment, right? We can do designs up front and say, this is what we believe, but in the end, it comes down to trying things and trying real scenarios and growing those as the scale grows. And to do that, we need acceleration of a wide form, right? We need acceleration for very specific tasks like GPUs accelerate machine learning and deep learning, or custom processors to do custom kinds of computations, buses or high-speed memory like NVMe. So there's specific acceleration capabilities that we can employ to solve key performance problems. I talked a lot about development today, and again, Agile is a part of this, but it's also, we need to design in future model approaches, and really microservice and API-based models are the direction that companies are using to define an application this complex at scale. We can't, again, write a whole big application as one and expect to be able to easily adapt it to this non-static environment. We need to be able to design an application where we can easily change parts and substitute parts when we find that they're not up to the task of dealing with scale. And I mentioned multiple times today that Agile is really key, and experimenting is really key to the models by which we solve these enterprise performance computing challenges. So with that, I'm just going to kind of summarize what we talked about today. We talked about enterprise performance computing and defined that as these modern workloads that companies are wrestling with, from AI to big data and analytics, image processing, but so many more, right? Bitcoin and blockchain, and there's so many of these technologies, and these technologies are primarily open source. They're being developed by companies that are sharing the source code in the public as open source code. And that's good for everybody. It's good for customers. It's good for partners to work together this way. And we're definitely seeing companies invest. If you look across the market, you can see companies investing in artificial intelligence, investing in big data and analytics. And again, in particular today, as part of the challenge of trying to sell in a very complex, I can't come into your office setting, we need to be able to deliver solid digital services to our customers. And the way to do that is really by creating these enterprise performance computing workloads. And that's what digital transformation is all about. It's about creating new services for customers. And again, that's two aspects. It's transforming the IT infrastructure in my company for operational efficiency and to be agile enough to handle the new challenges of these digital services. And then it's creating the services themselves. And the whole talk is enterprise performance computing. It's all about performance. We need to be able to do this at high scale. And so with that, I'm going to close by saying thank you very much for your time today. We really had fun bringing this information to you, and we hope that you had fun with us today too. Thank you so much, Brian Gartner, for sharing your expertise with us. Thank you for our team behind the scenes who have helped us pull this all together for you in this digital format. And again, we hope you enjoyed the presentation.